Hello viewers, today we are going to study about differential equations with variables separable form. Viewers, in today's lecture we are going to discuss the method of solving uh, the first order and first degree differential equations uh, which are uh, solved with the help of variables separable form. Clear? So let us first see what do we mean by variables separable form. Clear? Suppose we have a differential equation of first order and first degree in the form dy over dx is equal to say f of x and say g of y. Clear? Here f of x is a function of x and here g is a function of y. Now here we see that if we write this differential equation 1 in the form dy over g of y and f of x and dx. Now this form shows that we have separated the variables. Clear? And what are the variables here? X and y are the variables. Clear? Now here we have separated y to the left hand side and x to the right hand side. Now we integrate both the sides. Clear? Then we get integral of 1 over gy, and here we have integral of f of x dx, and we have the constant of integration as c. Clear? Now this integral and this integral can be evaluated by the techniques of integration which we have discussed in our previous lectures. Clear? So this is the algorithm of solving differential equations of first order and first degree with variables separable form. So viewers, let us take some examples to illustrate this method. Now here we have the differential equation dy by dx is equal to 1 plus y square divided by 1 plus x square. Now viewers, here we'll apply or we'll first examine the differential equation, and we arrived at the conclusion that this differential equation belongs to the variables separable form. So here we collect the terms containing x variable to one side and the terms containing y variable to the other side. So let us do it. So here we have dy over 1 plus y square. By separating the variables, now we have here dx over 1 plus x square. Now we integrate both the sides, so we get the integral of 1 over 1 plus y square. Here we have the integral of 1 over 1 plus x square, and c is the constant of integration. Now we know that the integral of 1 over 1 plus y square is tan inverse of y, and this is tan inverse of x, and here we have the constant of integration as c. Clear? Now this is the solution of or the general solution of, this is the general solution of this equation, say equation star. This is the general solution of equation this. Clear? Now this solution can also be written like this, y equal to tan inverse of x plus c. Clear? So this is the required general solution of the equation, this equation. Clear? Now here I would like to mention one more thing, that suppose we are given the initial conditions. Suppose we are given the initial conditions as say x is equal to say when x is 0, then y is say 1. Clear? Then what is the particular solution in that case? Clear? So let us substitute these two values in this solution. Clear? And when we substitute the value of x and y, our aim is to find the value of c. Clear? So let us substitute here. Here y is 1 and we have tan, and here we have tan inverse of 0 plus c. Clear? Now viewers, we can take tan to this side, so we have tan inverse of 1 is equal to tan inverse of 0 plus c. Clear? Now tan inverse of 1 is pi by 4 and tan inverse of 0 is 0 plus c, and this is c. So the value of the constant is pi by 4. Now we substitute this value of c in this equation. So therefore we get y is equal to tan of tan inverse of x plus pi by 4. So viewers, this is the particular, this is called the particular solution of this equation, this differential equation. Clear? And this is the general solution of this differential equation. So the general solution contains the arbitrary constant c, while the particular solution does not contain any arbitrary constant. Clear? So viewers, let us come to the second question. Now viewers, let us take this differential equation. Here we have y log y dx minus x dy is equal to 0. So let us first rearrange this differential equation, and we have y log y dx is equal to x dy, and from here we'll separate the variables, that is we will collect the x terms to one side and y terms to other side. Clear? So the terms containing x variable can be written as here we have dx over x, and here we have dy divided by y log y. So we have separated the variables. Clear? Now let us integrate both sides. So if we integrate, we have I am writing this term to the left hand side. So dy over y log y is equal to, here we have dx over x, and say c1 is the constant of integration. Clear? Now viewers, let us solve this integral. So let I1 is the integral dy over y log y, and we put t is equal to log y, and dt is equal to dy over y. So therefore this integral becomes dy over y is dt, and log y is t. So we have log of t. Clear? We have log of t. So this is log of t, which can be written as log of t is log of y. Clear? Now let us substitute the value of this integral as log of log y in equation say 1. Therefore we have log of y equal to log of here we have x plus c1 can be written as say log of c. Clear? Now here's this expression can be written as log of y. This can be written as log of cx, and this can be written as log of y is equal to cx. Okay, now this can be written as log of y is equal to plus minus cx, and plus minus c can be written as another constant, say k. So we have log of y is equal to kx. Okay, so this can be written as y is equal to e raised to kx. So where's this is the solution or the general solution of this differential equation. Clear? Now viewers, let us take this problem. Find the general solution of the differential equation log of dy by dx is equal to ax plus by. Now viewers, here we have the equation log of dy by dx is equal to ax plus by. Now this equation can be written as dy by dx is equal to e raised to ax plus by. Why? Because if we have say log of say t is equal to say some number p, then t can be written as e raised to p. Clear? So here we have used this result. Clear? Okay, now we can write this differential equation in the form e raised to ax times e raised to by. Now applying the variables separable form, we collect the y term or the term containing y variable to one side. So we have e raised to by, and here we have e raised to ax times dx. Now this can be written as e raised to minus by dy is equal to e raised to ax dx. Clear? Now if we integrate both the sides, we have e raised to minus by dy is equal to e raised to ax dx plus say some constant c1. Clear? Now the integral of e raised to minus by is e raised to minus by divided by minus b, and here we have e raised to ax divided by a plus c1. Clear? Now we can write or we can rearrange this equation by multiplying throughout by ab. Clear? So we multiply the both sides of this equation by ab, then we get minus of a e raised to minus by is equal to b e raised to ax plus AB times C1. Now this is another constant, and let us say it C2. So this can be written as minus A e raised to minus by is equal to b e raised to ax plus C2. Clear? So here's this is the general solution of this differential equation. Now we can arrange this equation like a e raised to minus by plus b e raised to ax plus C2 is equal to 0. So this is the general solution of this differential equation. Clear? Now viewers, here we have the differential equation cos of dy by dx is equal to a, where a is some real number, and we have to solve this differential equation when y is equal to 2 and x is equal to 0. So this differential equation can be written as dy over dx is equal to cos inverse of a. Clear? Now this cos inverse of a is a constant, and say let cos inverse of a can be written as say p. Clear? Because this is a constant here. A is the real number and cos inverse of a is a constant, and let us assume cos inverse of a is equal to p. So we can write it as p. Now this equation can be written as dy is equal to p dx, and if we integrate both sides, we have integral of here we have dy, here integral p dx plus c. C is the constant of integration. Now here we have y, and here we have px plus c. Clear? Now this is the general solution of the given differential equation. Now here our aim is to find the value of c by making use of the given values. So here y is equal to 2, so we substitute y is equal to 2 when x is 0 in this equation. So we have 2 p times 0 plus c. So we have 2 is equal to 0 plus c, so c is equal to 2. Now we substitute c is equal to 2 here, so therefore we get y is equal to px plus 2. Now again resubstituting the value of p, we have x cos inverse of a plus 2. So this is the particular solution of this differential equation. Clear? Now viewers, here we can also express this solution as y minus 2 is equal to x cos inverse of a. This can be written as y minus 2 divided by x is equal to cos inverse of a, or cos of taking this cos inverse to this side, we have cos of y minus 2 over x is equal to a. So this can also be one of the form of this equation. Clear? Now viewers, let us take this problem. Find the particular solution of the differential equation dy by dx is equal to 1 plus x plus y plus xy, given that y is 0 when x is equal to 1. So we have this differential equation. So viewers, let us write it as dy over dx. We have 1 plus x. Let us group the terms here and take y common from these two terms. We have y 1 plus x. Now if we take 1 plus x common, then we have 1 plus x times 1 plus y. Now viewers, from here we can separate the variables, and we can write dy over 1 plus y, and here we have 1 plus x dx. Clear? Now we have separated the variables here. Now let us integrate both sides. Now we have the integral of 1 over 1 plus y. Here we have 1 plus x dx plus c1. c1 is the constant of integration. Now the integral of 1 over 1 plus y is a log of 1 plus y, and here we have x plus x square by 2 plus c1. Clear? Now we are given that y is equal to 0 when x is 1, so we substitute here in equation 1. So we get log of 1 plus 0, and here we have x is 1, we have 1 square over 2 plus c1, and log of 1 is equal to this is 3 by 2 plus c1, and this can be written as log of 1 is 0, so we have 0 equal to 3 by 2 plus c1, and c1 is minus 3 by 2. Clear? Now this is the value of the constant of integration when y is equal to 0 and x is equal to 1. This is the general solution. Now if we substitute the value of c1 as minus 3 by 2, so we get log of 1 plus y is equal to x plus x square by 2 and minus 3 by 2. Then this represents the particular solution of this differential equation. Clear? So this is the general solution and this is the particular solution. Now viewers, let us take this problem. Find the particular solution of the differential equation e raised to x multiplied square root of 1 minus y square dx plus y over x dy equal to 0, and given that y is equal to 1 when x is equal to 0. Clear? Now here let us rearrange or let us rewrite this equation as e raised to x multiplied square root of 1 minus y square dx is equal to minus y over x dy. Now let us separate the variables, and we have e raised to x dx. X we take x to this side, or we multiply x to the left hand side, and then we have minus y, and here we have integral a square root of 1 minus y square dy. Clear? So this is how we separate the variables, and we collect the terms containing x variables to the left hand side and y variables to the right hand side. Now viewers, let us integrate both sides. So we have here integral of x e raised to x dx, and here we have minus integral of y divided by square root of 1 minus y square dy, and c1 is the constant of integration. Clear? Now viewers, here we have to integrate this integrand with the help of integration by parts. So let us denote I1 as integral of x e raised to x. So let us apply the concept of integration by parts. So this is the first function. So we have x, then integral of e raised to x minus integral, then the derivative of x, and then integral of e raised to x dx. Clear? And here we have dx. So we have used the formula for the integration of parts. So we have x, integral of e raised to x is e raised to x minus, here we have 1, integral of e raised to x is e raised to x, this is dx. and then we have x e raised to x minus the integral of e raised to x is e raised to x. Clear? Okay, now the integral of this term is equal to this. Clear? Now if we integrate the second integral here, let us assume it as I2. Clear? So I2 is y over square root of 1 minus y square dy. Clear? If we substitute t is equal to 1 minus y square, we have dt is equal to minus 2y dy. Clear? So dt over minus 2 is equal to y dy. Now integral I2 can be written as this is dt over minus 2 divided by square root of 1 minus y square, and we have square root of t. We can write it as minus half integral of minus half dt t raised to minus half. We have minus half t raised to minus half plus 1. We have minus half plus 1. So where's this is minus half, we have t raised to half, we have half here. Half and half get cancelled, so we are left with minus of square root of t, and this can be written as minus of square root of 1 minus y square. Clear? Now let us substitute the value of I1 and I2 in this equation. So we get we get x e raised to x minus e raised to x, and here we have minus of minus square root of 1 minus y square and plus c1. Clear? So this can be written as x e raised to x and minus e raised to x and plus square root of 1 minus y square plus c1. Clear? So this is the general solution of this differential equation. Now let us find the particular solution of this differential equation by substituting y is equal to 1 and x is equal to 0. So if we substitute x equal to 0, we have x is equal to 0 here. We have 0 times e raised to 0 minus e raised to 0, and here we have 1 minus 1 square plus c1. So this is 0, this is minus 1, here we have 0 plus c1, so where c1 is equal to minus 1. Now we substitute the value of c1 here, so therefore this equation becomes we take e raised to x common, and we have x minus 1 is equal to square root of 1 minus y square minus 1. So this is the particular solution of this differential equation. Clear?